Hi, this is Lex, and welcome to the FinTech Blueprint. It's your podcast about fintech, decentralized finance, digital banking, investing, robo-advice, artificial intelligence, and all the other frontier technology that is transforming financial services. To get more content, like an illustrated transcript of this conversation in your inbox, subscribe at fintechblueprint.com. So without further delay, let's jump into today's episode. Hi, everybody, and welcome to today's conversation. We have an absolutely fascinating topic today with Jason Morton, who is the founder and CEO of EZKL. EZKL is a technology that helps people build around artificial intelligence using ZK proofs and the latest in technology. So we'll open all of that up. Jason, I'm so excited to have you on the podcast.
Good to be here, Lex.
So maybe just to get us into the mood, how did you enter the industry, or how did you enter the space? What is your background? Where do you come from? And what do you focus on?
Yeah, thanks. So very long road. You can think about what we do today as taking an AI model or a statistical model, turning it into a system of polynomial equations, and turning a crank to get cryptographic proof out of it. My area of research, I have a PhD in math, and I was a math professor. My area of research was something called algebraic statistics, where we did exactly that. So we took a model, whether an AI model or a statistical model, and thought about it in terms of algebraic geometry, in terms of systems of polynomial equations. And so that led, actually the first time I tried to do that was around 2008, when we wrote a paper about deep Boltzmann machines. I had this meeting with Andrew Ng, and he told me that deep learning was the new thing, and people were thinking about putting it on GPUs and all this stuff. And so got started working on it back then. It was more of an academic exercise in some sense at that point, because we didn't have a really great reason to turn it into a system of polynomial equations except to study it. And so it's been exciting recently because suddenly that kind of thinking lets us do a lot more with models in terms of verifiability and privacy.
During that moment, for example, what was your motivation like? Is it the difficulty of the problem, or the research areas unexplored, or is it, some greater aesthetic pleasure from being able to do this? What drove you to pursue these topics in the first place?
Yeah, so back then, it was some combination of just real liking the math itself, right? And having studied algebraic geometry and this kind of way of thinking about things. And some matter of kind of conviction that automated decision-making, automated reasoning, AI would be really important in the long term, and wanting to make some kind of contribution to it. I think I'm not a great, or at least at that time I realized that I was not a great kind of engineer of these systems in terms of solving the kind of machine psychology problems or the soft problems. But I wanted to contribute in a way that could happen from someone who comes from a more mathematical point of view.
That's 2008, probably 6 years before any of the neural networks are hitting production in the large tech companies. What was your path like between then and maybe the first instances of seeing the magic that machine learning systems started to bring forward?
So that was, as you mentioned, way before, before it was happening on GPUs. Before, I think there was a lot of window into it being really important. So as part of this DARPA program that was in 2011, it was like a deep learning program with Jan LeCun and Andrew Ng and Joshua Bengio and folks like that. And, as the mathematician, my job was, these systems seems to work in practice. Do they work in theory? So we were trying to get some theoretical results that showed that they were doing something new. Because at that time, they were very promising, but they weren't quite to the point where they could outcompete specialized solutions, right? So it could do face recognition, but not quite as well as a Haar cascade or something like that, right? So not quite as well as a special solution, but they had this kind of glimmer of generalizability, and so people were excited about them. And worked on that again from the mathematical point of view, proving some properties of these things, and then kind of wandered off a bit just as it got to be commercial, because at this point I'm still an academic, and it became very difficult for anybody in the academy to compete with big tech, right? I think my last NeurIPS was the one before Zuckerberg showed up and money started getting thrown around, right? And at that point, I think there was a big divergence in terms of what could happen in university and what could happen in industry. And I ended up focusing on some other types of problems that were related, since the time on quantum information and studying circuits from sort of high level using category theory and stuff. And that was well into the kind of late 2010s.
How do you pick the problems that you focus on? Because you're like very casually, describing.
No, it's just kind of, it's like a search, it's isn't this cool? And then something pulls you down the path. It's a very random walk, to be honest.
Is it a novelty search?
Yeah, it's a novelty search. Sometimes you have a hammer and then you look for a nail, and sometimes you have a problem and you look for the right hammer to solve that problem. It sort of bounces back and forth. Yeah, and then I sort of, at the same time in the background, there was the cryptocurrency blockchain stuff happening. I think my first attempt at that was trying and failing ultimately to buy some Bitcoin on Mt. Gox around 2011. And then kind of losing track of that for a little bit until Ethereum came out. And then I got really excited about that space again. And these threads didn't really come back together for me until, so there was some stuff on that side, but they didn't really come together for me again until the ZK started to become important in Ethereum and in blockchain generally as a way to make things more private and make things more scalable. And at that point, it's kind of, okay, this problem of how do you mathematically decompose statistical models, AI models, into their constituent kind of polynomial systems, and how do you get them to work with blockchain, converged again. And so that was actually when I stepped away from academics and put my energy here.
So let's start with the basics, which is ZK. What is a zero knowledge proof and why are they important and useful?
Yeah. Okay. So my favorite way to explain what a zero knowledge proof is, so they've gone through lots of different ways of presenting them. And when I first heard about them at an Air Force meeting in 2015, I didn't get it at all because the scenario was something like, you want to run a computation on the Amazon cloud, but you don't trust Amazon. And so you ask Amazon to do this thing with 1 million times overhead and you get the result, right? And in that model, it felt, and by the way, it's probabilistic. There's a chance that it won't actually be correct. And that felt kind of crazy because if we don't trust Amazon, we might as well turn off the internet, right? Everything runs on these cloud servers. And so that was hard. And that was sort of the publicly checkable proof era. And then I think the best way to think about it is as a generalization of a digital signature. So, if you know what a digital signature is, and not everybody does, but it's a good sort of starting point. Digital signatures underlie, of course, blockchain transactions, but also things like when how you know when you go to a website, genventures.xyz, that it's really the one. That's what gives us the lock symbol, is a hierarchy of signatures, digital signatures, both TLS and everything else, but to know that it's the right site. So take a digital signature. You have as inputs, like ECDSA, you have as inputs some message that you're signing, really the hash of that message, and you have a private key. You have a signature algorithm, which is generally very simple, from exponentiation, elliptic curve operation, or RSA. You run this algorithm and you produce output, the signature, and then anyone can take that signature, and maybe with the message hash, and believe that you really knew the secret. The secret kind of identifies and authenticates you. You really knew that secret. You really ran the algorithm combining that secret and message hash to produce the signature. So there's a belief or a proof that you really knew that secret. You really ran that algorithm. And the weakness here is that the algorithm itself is fixed once and for all. And the private input is limited to this high entropy private key. And when I think about a zero knowledge proof, is a generalization of this. So it lets you take that signature algorithm and replace it with any program in the world, any program you might ever want to run. And it lets you take the private input, the secret key, 256 bits or whatever, and replace it with as large a private input, arbitrary private input you want. It can be your tax documents, it can be your face, it can be a movie, it can be whatever you like, and the public information as well. And it combines those things and produces, instead of a signature, what we call a proof, which has the same property that anyone can look at that proof and believe that you really ran the algorithm that you committed to on these inputs. You really ran the algorithm we agreed upon ahead of time, and it showed that this was a video of, a cat taking a bath or whatever, or something more consequential. So yeah, that's how I think of zero knowledge proof. It's very much like a digital signature. It's a programmable digital signature. It gives us a lot more power.
One question, and again, from a very naive point of view, is what does this give us just on the digital signature side? Or, the flip side being, if we didn't have this, what would be missing from the internet and our digital experiences?
If we didn't have digital signatures, or if we didn't have this proof?
If we weren't able to have, the SSL lock next to the URL, and if we weren't able to use zero knowledge proofs, like what is the thing that people would not have in their day-to-day experience?
Digital signatures alone kind of mostly give us an authentication. This person said that such and such was true. Without that, there would be no way of knowing that the site that you're going to is the real site. So it'd be very easy to send you to a fake Google or a fake copy of your bank or whatever and trick you. So there would be much less security online. The entire blockchain system as we know it wouldn't work because there'd be no way to sign transactions. There'd be no notion of a wallet. And even things like credit card payment systems would, I think, struggle to operate. So there's a lot of signatures that happen and deep in the sort of bowels of your computer to make authentications and handshakes work. And those would all stop working, basically. It's similar to, what happens if someone comes up with a quantum computer and all these things break. And what's kind of interesting is that we've built all of that, this sort of security infrastructure of the internet, and enabled transactions and enabled so much commerce to happen over the internet. We can have Amazon, we can do all this stuff. Right? And we've done it all with signatures, with non-programmable signatures, by building these kind of complex hierarchies of operations and trusts and revocation. I authorize this. I authorize this key. I can revoke this key. You have this whole complex system, and we're sort of programming with signatures instead of programming in signatures. And what zero knowledge proofs really unlock is the ability to program in signatures. So you can take one of these big complex systems built as a primitive, and in theory, at least, potentially replace the entire system with just a program. So instead of, you want to do a new protocol, instead of hiring a cryptographer and spending a couple of years, you just write the code, compile it, and it's done. I think we're only in the very, very early stages of seeing what happens when we change that. So I mentioned the affordance of authentication. What they also give you is sort of two things: privacy, which is sort of the new element. So in a typical digital signature, you get exactly one thing that you get to keep private, which is your private key, right? Everything else about the message is not private, or at least the hash of the message is not private. So there's not like a specific way to do that. And what these let you do is you can choose parts of the message to reveal and parts to remain private. So you can say, for example, go through a KYC process and say, well, I'm not a member of a group that's not allowed to do this, or I am a member of a group that is allowed to do this. And that's all you get to learn as the other side. And then the other piece that it gives you is kind of validity, which is the one way to think about, okay, we ran this program. One person ran a program, produced a proof. Now everyone in the world can believe that that program ran successfully. So even if there's a high overhead, if many people are trusting that, verifying that that program ran correctly, that overhead gets kind of amortized for all the people. So it's kind of an alternative to consensus, right? So in consensus, we run the same program many times. Here we run the program once, and everyone else just trusts that it's true because they can verify that it's true, rather. Yeah.
That is the punchline, 100%. Just playing it back in the way that I understand it, and correct me if I'm wrong. So the first bit, which is essentially encryption, is the authentication and identity math that the entire internet is built on. Whether it's directing traffic to a website, or knowing that you're inside of a shopping cart, or sending your credit card information in a secure way, that's built on digital signatures. And the next step around zero knowledge proofs is that they can be made multidimensional and programmable. So the example that you gave of proving that you're a member in a group, so that's you want to get into a bar and they want to card you, but instead of having to show them, your whole passport or driver's license, you're able to show a proof that says, yes, this person is over 21 or over 18 if you're lucky enough to be in Europe. You don't have to reveal everything about yourself. You just can reveal the one attribute that the counterparty is interested in. And if that's right, my next question to you was going to be, what does zero knowledge proofs do for blockchains? Because, before we even get to ZK machine learning, there's been a ton of work building rollups that are using ZKs as part of their process. And you had mentioned that it's potentially a better mechanism for achieving programmable truth and trustlessness than consensus. So can you spend more time opening that up in the sense of like, option A is game theory plus money equals consensus and what that does, and then versus the zero knowledge approach and what that does, and how you're seeing these things play out in real time?
Yeah, so there's a bunch of those directions that we can go here. So one of the ways you can think about it is that the kind of validity you get from ZK is almost orthogonal to the kind you get from a consensus, blockchain consensus mechanism, right? So you can use it to scale blockchain so that you can have new operations, more complex operations that effectively run as though they ran on-chain, right? You want to run your AI model on-chain, or you want to run a rollup, you want to access history, all of those things become possible. But it's also interesting, you brought up the game theory, because it's a way of securing that doesn't rely on fraud proofs or on game theory at all, right? And so there are a lot of, so step back in time for a second to sort of 2017, 2018 period, right? Like people were really excited about blockchain enterprise, right? Let's try to use this new idea we have around impossible to forge transactions and contracts and consensus to try to replace some of the systems we currently use for things like settlement and ERP or whatever, right? And part of the problem with that, I think, was that if you rely on game theoretic incentives, you really limit your audience a little bit, right? So there's economic issues around you can't secure something of much greater value with much lower value, and there are some things that are just inconceivable. So, for example, if you have, and this is getting a little bit far with the question, but okay, so one of the things that comes up a lot is there's optimistic, let's skip forward a little bit, there's optimistic approaches to machine learning, right? Where you do fraud proof instead of doing a proof of execution of the algorithm. And that, of course, requires that you have a game theoretic aspect. But there are many adversarial settings or settings in general where you don't really have the ability to rely on that. So suppose you wanted to, you're talking about a drone or something, and the drone is analyzing an image and trying to decide whether or not to take an action. You can't have this, it's not an economic decision that the thing is making. Does that make sense? And it's sort of almost inconceivable that you would delegate it to that. So I think the same thing kind of happens, that's a bit dramatic, but the same thing kind of happens in corporation or in kind of what are currently off-chain corporate activities. You may have a need for confidentiality, you may have a need for validity, and the people involved are not comfortable delegating it to a game theoretic mechanism outside this traditional legal system. In those cases, you can do a cryptographic mechanism.
Got it. So if I were to characterize it, it would be the consensus mechanism, the game theoretic mechanism is you've got some sort of economic incentive or exposure to be honest. And if you're dishonest, you get massively punished. And usually the way that it works with Bitcoin or Ethereum and other networks is the more people are playing the game, the more secure that consensus mechanism is. So the bigger the chain, the more likely that the stuff on it is actually true. But with ZK, you don't need to avail yourself to like the guessing game and this economic competition. You can just derive whether something happened or didn't.
One of the other things that follows from that is speed. So I also did some work on MPC systems and, of course, blockchain systems. Anything that requires consensus or communication has this fundamental limit around the speed of light, right? If you have agents that need to communicate with each other and those agents live on a network, and they're 100 milliseconds away or 300 milliseconds away from each other, and they have to do some round trips. You can only ever go so fast, right? You have to wait for block times or fraud-proof periods. That's further limitation. In the beginning, it looks like those things will be faster than ZK, right? Because the ZK overhead is significant, although it's declining at a really fast rate, like much faster than Moore's law. But the fact that you don't have to communicate means there's kind of no speed limit, right? So if you can parallelize it or you can improve your algorithms, you can get to that kind of finality using a zero-knowledge proof as fast as you can compute the proof, right? Whereas in the other case, if you always are going to have to do some communication, you always have to wait for that discussion to happen.
Why is it hard to compute the proof? Why does it take a long time today?
So there are fundamental reasons, and then there are sort of practical reasons. And I think we've found, we've sped up our system by, I don't know, something like 20,000 or 30,000 times since we started, something like that. Most of it is honestly because these things are magic and a bit of a miracle, and they only just barely started working. Right? So like only in the last couple of years did we get to a system that would do anything non-trivial. And whenever you're doing an engineering problem, right, it starts out with kind of high unit cost, it's slow, it's very manual, and eventually it gets faster and faster and it gets cheaper and cheaper. And the same thing happens here. So most of the ZK systems that are in production today, I would say including ours, like just kind of barely work, right? And so a lot of the work that we're all doing is you go back to a system that works and then you find all the bottlenecks, you remove them. So it's just kind of piece by piece engineering. I think there's a lot of times people are searching for a silver bullet, looking for the new proof system or looking for a new idea that will solve all the problems. But I think it's largely really a lead bullets discipline. It's just tuning. You're trying to make a car go fast or a rocket go up. You're removing pieces from that, making things thinner. And that's the process. And that process just takes time.
So let's move to machine learning and what brought you back to looking at the AI space, and then what is the current thing that EZKL is focused on?
Yeah, so there's a couple of affordances that we get here. So one of the questions is, or one of the things you might want to do is, in the context of blockchain, to run an AI model as if it ran on chain, right? Or now increasingly there are more and more projects in the area that introduce some sort of economic incentive there, right? Token incentive or the ability to incentivize creation of models, execution of models. So one of the most fundamental things you need to be able to do there is to check whether a model was run, promised model was run correctly. And can we make it as though it ran on chain, right? And that the way you do that is to commit to the pieces that you need to commit to and finally verify it. I think we're thinking about that, of course, a lot. I'm working with folks, but in general, we're also trying to think about what are the broad areas in which verifiable AI makes sense. And there is an overhead. As I said, I think that overhead is coming down very fast. I think in 10 years or 20 years, maybe, we might be able to say that overhead gets down to less than 2 times, right? So, or even something like 30% or something, who knows? Could be sublinear. I think in long term, it'll be a little bit like ECC RAM, right? There's an overhead for ECC RAM that costs a little bit more. Maybe it's not quite as fast for the same price, but what you get is a higher degree of certainty. I think maybe long term, it'll be almost a cost you can ignore. So we're thinking about, okay, what are the scenarios? But today, before we get there, what are the scenarios in which we want to be able to run a statistical model? We want to be able to run an aggregation or a query. We want to be running an AI model. And there's enough of an adversarial environment that it's worth the motivation. People are motivated to have this kind of cryptographic security. So yeah, I guess that's kind of the explorations that we're doing with various customers in different areas, is both who needs it, right? Who needs that kind of security today? And then how do we provide that kind of security? And one of the other kind of questions that this brings up, and which we find is really, really important in moving toward production with any of these systems, is that you are designing a crypto system, right? You have some things that are secret, some things that are public. You have some pieces that are checked, some pieces that are not checked, and figuring out how all those things should plug together in order to produce a system that is trustworthy and economically useful is a really difficult kind of Cambrian explosion of possibilities design problem, right? It's like someone gives you the internet and you're trying to figure out, what is the internet for? What can I do with it? Is it for sharing cat pictures? Is it for something, And so sometimes I think what we're doing in ZK, like us, but other people too, right, is it's almost like we're trying to invent a web framework, right? You go back to the early days of the web, we had C, we had all the pieces, like we had Java, early JavaScript, like we could have made web applications. You could have made Gmail or something, right? You could have made all these other web applications that we've seen, but people didn't yet, partly for performance reasons, but also partly because we lacked the abstractions of kind of MVC or 12 factor or all the different, where does data go and stateless statefulness and React and components and all this stuff, right? We just lacked all those abstractions that made developing that kind of application easier. And we're definitely in this stage where we're trying to figure out the right abstractions people can understand and build with them. One extreme of that is all you get is signatures, right? And you can use that to build really impressive systems. The other extreme of that is, here, I'm going to hand you a verifiable computer, a VM or a trusted enclave, do whatever you want, right? And I feel like both those extremes are kind of not the right path forward. We have to figure out the thing in between that has the right abstractions and the right interfaces that let people build, economically valuable things with it.
The way that I understand, or at least my cartoon version of it, is we have these two separate technology trends that are both mathematically driven, but from very different parts of mathematics. And one is the blockchain as a computer, and at least in its current form, it's a tiny computational bandwidth that can go in there. So it's like everybody wants to have the Mandalorian rendered in the Unreal Engine, but right now we have the Nintendo with maybe like 4 colors in it, and then on the other side, we've got these unbelievably hungry statistical models, as you say, right? Like trained on an absurd, like for hundreds of millions of dollars on the entire internet, running on supercomputer clusters, like incredibly resource intensive, but they're able to produce kind of labor and economic activity. And so we have like the Nintendo version of economic architecture and then the alien version of intelligence, and trying to connect them together is really, really difficult. So how do you transform and compress the stuff that's happening off chain to be non-corrupting and to be true on chain as well? And what kinds of models have you seen, like machine learning or generative AI, that you think that maybe are the first use cases for EZKL, the framework to do this, where you're seeing some demand and you're like, okay, that makes sense. That AI stuff should live on these blockchains, and this is at least a glimmer of what's coming.
In terms of the scope of the model, I think everybody wants LLM, right? Like big LLMs. But a little bit that's just because that's what's in the moment. It's kind of the exciting thing in the moment, right? I think those are coming reliably, and because we get much faster than Moore's law, kind of how many cycles we get or how much proof we can get, that doubles at a much faster rate than the size of the models, even though those are also getting big quickly. Those will all be possible. But I think it's more interesting today to look at the kinds of models that are the kind of statistical ML decision models that are deployed in the world today that are making economic decisions, right? So that might just be something as simple as a regression or a decision tree or a small neural network that's producing prices or making classifications. Those kind of things are eminently practical. They can be proved in a few seconds for the most part, and I think are a great way to reveal the kind of problems that make sense. So, for example, we have seen some LLM stuff with EZKL. We're also looking at people who are doing things like credit ratings or aggregation. So we're working on a project which is a simple aggregation of votes, right? So they work with Optimism, who gives away a certain amount of money every, it was 120 million last time, periodically. And what they do is collect ballots from badge holders, from voters, privately, and then produce from that an aggregate, run it through an algorithm, and that decides how much money each project gets. Right? And so the algorithm we put into EZKL, And that lets you kind of preserve the privacy of the voters in two directions. One is that who you voted for doesn't become public, and the other is that you have no way to prove you voted for a certain person, or for a certain project, which would subject you to the possibility of bribery. So that's a very simple algorithm. It's just an aggregation. It's almost like something you could do with data frames or with a SQL query or something. But it's nevertheless kind of economically important. So we look for those kind of examples right now to get a sense for where the demand is. We also see a fair amount of stuff in DeFi and games, because for example, in DeFi, what you can do is you commit to a vault, commit to a strategy, have a vault around that strategy, let that run for a while, show some performance. Anyone who puts into that same vault can be convinced that future executions will follow the same strategies. There's no risk of strategy drift or rugs that are not built into that original model.
If you could open that up a little bit more, let's say there is an investment strategy and there's a box, and the box says, put money into here and I will do XYZ. I will go and invest in NFTs with the color red, and that's the only thing I do. How does lacing in proofs work in that case? Like, at which part of the smart contract, or like, how does that integration happen?
Yeah, so the high level view is basically you submit to the smart contract. You can think about it like a trade or a state transition. You say, here's the inputs, here's the outputs, here's the proof, right? And then the smart contract runs the verifier. It checks that the inputs are still true. And then if they are, it changes them to the outputs, right? So maybe it's just portfolio weights or something, right? In that case, you don't really need the inputs. But maybe you have, as an input, you have something like, what block are we in? Or what are some prices or something? And so it's really just it's almost making a lookup table or proving the execution of a function, proving a state transition, any kind of state transition.
For people who are not as versed in blockchain in this space, like I go back to the example of Ray Dalio and Bridgewater, and like the Ray Dalio claim is we use a gigantic global macro model with thousands of inputs to figure out what decision we're making. And there's like a book recently written on it, as well as a New York Times expose, which basically says like there's 100 rules in an Excel file that Ray Dalio picks from. And that's how it works. So in that case, you'd be able to say, okay, well, if you do have this enormous global macro model, plug the wires into the prover and it would actually validate for you whether that thing is being used or whether it's a dude with a spreadsheet.
Yeah, absolutely. That's a really interesting direction, I think, is that we would like to explore around specifically asset management and kind of aspects of due diligence, right? You have the asset manager, they say they have a sophisticated quantitative model. You can kind of prove whatever properties you like about that model, like how many factors are being included, or what is the leverage of each of those? Is it really 100? Another kind of even more stark version of this is there are many quantitative strategies, which as an LP, you ask yourself, is this alpha real or are they just selling puts? Because selling puts looks fantastic until it doesn't, right? And, not literally selling puts, but implicitly selling puts, have a strategy that's equivalent to that. And it's really interesting to explore that kind of thing. It doesn't necessarily have anything to do with blockchain, of course, because that need to prove some capabilities that you have or some facts about your company without revealing all the details about your company is a very common situation. I think that's also really relevant when we think about privacy. So usually when people are thinking about ZK and privacy, they're thinking about individual privacy around, my my PII or my transactions, like wanting to hide my transactions. And of course, those things tend to be controversial because governments don't tend to be crazy about it, and also because economically, it seems like people are rarely willing to pay for privacy. I think the right place to think is actually more on the corporate side. And you say, while humans an individual may not be willing or even legally allowed to maintain their privacy, if you go to the level of a corporation, they often have an obligation to maintain confidentiality of other people's private information or their own internal trade secrets, or they want to convince the financial markets that their sales was X and their profit was X without revealing all the details. So they hire human auditors to check those things. But we could do the same thing with ZK. Right? So one way to think about ZK is that it's a way to and the kind of stuff we're doing with EZKL is that it's a way to remove trusted intermediaries and do something that's a lot cheaper.
It's a way to actually know the truth as long as there is some sort of digital substrate in which it floats.
Right. You have to have a source of truth there. And so that's part of the reason this whole thing takes time, because like HTTPS spreading throughout the internet, nobody else is doing it. It doesn't necessarily add that much value when you do it. But I think it does have natural network effects once it gets rolling.
So what is EZKL itself? I know it's a company, and I know that you work with other developers and they pick up pieces of it. Like, how do you think about it? Is it a product? Is it a set of libraries? Is it a framework? And then how do people engage with it?
So it's all those things. I mean, I think the best way to think about it is in terms of, if you're I bet that you can use it as a library or as a compiler. I think as time goes on, we move more and more to more complete solutions where you have a scenario that you want to accomplish, and we've sort of thought through components of that ahead of time. The way to think about it is kind of towards new ideas around sources of truth, analogous to something like a database engine, right? So it enables you to kind of transform one type of truth into another. That's a generically effective thing. But just to be really more concrete, okay, so how do you interact with it today? You have the following options. You can download the command line tool and you can create proofs and manage them. We have a backend proving service where we'll keep track of the artifacts and execute proofs for you, which is designed to be very fast and tuned based on what we've learned about the systems. And we have Python. So a lot of people the first point of contact is that they have a model that they've built in PyTorch or TensorFlow or scikit-learn, and they would like to prove that model. And you can just pip install EZKL and do that.
What's the economic or commercial model for what you're building? Are you thinking about this as like a product, as a protocol, as a giant open source layer?
So right now, the strategy is that this is a company. This is not a token product-based protocol. And so our sources of, the way we make money is either licensing some components of the system, running these backend services for folks.
And then when it becomes internet scale, what does that company look like?
As we grow, we'll be doing more and more of the work. So early on, our earliest users were kind of our most technically sophisticated in some sense, right? We can just hand them something that barely works and then they can build with it. And as time goes on, what we have is something that's more and more complete. So I think over time, it's going to look more like the kind of experience you'd have interacting with a hosted database system or a hosted accounting system, depending on, or a inference service, depending on the application.
Have we seen companies like this before? If you were to compare it to, something else out there, what does it look like?
Yeah, I sometimes think of it as a bit like something like Mongo or Kafka or Confluent in terms of that's for the database analogy, right? Or even something potentially like that's a sidecar to your AI workflow, MLOps company like Weights and Biases, or, in the most ambitious moments to something like an ERP.
Do you think most of the demand will come from, this is a bit of a rhetorical question, from Web3 companies or from Web2 companies, or this distinction not even makes sense once everything has grown up?
Long term, the demand has to come from real economic activity. Sometimes we get a little bit ahead of ourselves there on the Web3 side. So that means that I think long term, the demand for what we're doing and for ZK in general comes from enterprise and Web2, either in Web3, but kind of growing into those economic roles, right? So you take a company like Uber, say, right? Hard to predict today whether it will be Uber running this kind of stuff somewhere in its infrastructure or whether someone else will end up disrupting it coming from a pure Web3 side, right? Same with social or anything else. And I expect that there would be some mix of that. I do think it's a bit like an internet type technology, a verifiable internet or verifiable exchange of information, and that over time, more and more of the economy will touch it. You can almost think about it as a vector by which Web3 ideas expand to a larger economy that it has not been able to puncture yet.
Super interesting. I agree with you in that it's almost impossible to predict where demand will come from first, and there's just so much growth to be done in the AI space as well as the Web3 AI space that I think it'd be much better for our whole kind of niche to be open to each other and not start drawing these religious lines in the sand before anyone's even come into the party. You do have to go kind of really broad and open, and I very much appreciate that point of view. If our listeners want to learn more about you or about EZKL, where should they go?
Best place, I guess, the website, EZKL.xyz.
Fantastic. Jason, thank you so much for joining me today.
Great talking with you.
Hi, everyone. That's it for this week's episode of the FinTech Blueprint. For more technical deep dives into all things FinTech and decentralized finance, check out fintechblueprint.com and grab a free subscription to the newsletter. This is Lex, and I'll see you next time.